This is a lesson for Chapter 8, Section 7, titled Factoring Special Cases. So we have two different types of cases that we're going to be looking at here. It looks like a regular old factoring problem, and if I was to factor it, again, I'd do the same thing I had done before. See, I'm looking for numbers that multiply to make d squared. It has to be d times d. And then I look at that last digit sign, it's positive. It tells me the outside terms and inside terms are going to end up adding together to make negative 22. Well, it ends up being the same sign again, so negative and a negative, and 11 times 11 makes 121, and notice how the outside terms and inside terms make negative 22 when you go ahead and add them together. And so what we see here is we've got ourselves a binomial that's being squared. They're the same binomial, and so that's what we're going to end up seeing on some of these problems. Now, what we'll end up noticing, if it is a binomial square, is that the first term here and the last term are both perfect squares. Perfect squares and positive. And positive. And so the other thing that we're going to end up noticing about a binomial that's being squared is that the outside terms and inside terms are the same. So once you find one, if you double it, you can check to see if it matches the middle term. So on this one here, I notice again, p times p makes p squared, so that's a perfect square, and 144 is a perfect square. And I know that both signs need to be negative because the outside and inside terms add to make a negative. So I'd use p times p and then minus 12 and minus 12. And you see it works because p times p makes p squared, negative 12 and negative 12 make 144, and check the inside terms. They make negative 12p. Outside terms, same thing, negative 12p. And so you see if you double one of them, you get the middle term, negative 24p. So that's what it is, p minus 12 quantity squared. So on this one, same thing. We've got a perfect square here, and 1 is a perfect square. So I'll go ahead and take the square roots of those, and I'm going to do 7n times 7n makes 49n squared. Both signs are positive this time because they multiply to make a positive, the last terms do, and the inside and outside terms add to make a positive. 1 times 1 makes 1, and check out the inside terms and outside terms. See, 7n and 7n add to make 14n. So it does end up working out, so it's going to be 7n plus 1 quantity squared. So again, these are the answers. Let's take a look at that last one, though, and it looks like there's a common factor. Now, this is a perfect square and this is a perfect square, but sometimes they're not. But you could take out a common factor. That's always what we want to do, is factor completely. Try to find that perfect factor, and 25 is it. See, if I make 25, pull that on the outside, do some division, I'm left with j squared plus 4j plus 4. And we still have perfect squares on both the first and last terms. And so when I go ahead and factor it, I'm going to try j times j makes j squared. Both positive signs because they multiply to make a positive and add to make a positive. And 2 times 2 makes 4. So check those outside and inside terms. See, 2j and 2j. Those two j's add to make 4j's. So it does end up working out. So I would write it as 25 multiplied by j plus 2 quantity squared. So it's a special case that makes factoring easy, especially when you have big numbers like this, like 49n squared. 1's not too big, but if this were like 36 or 49, it would seem kind of tough. But if you see two perfect squares as the first and last term, then try it. See if it's a binomial that's being squared, or a perfect square trinomial, they could call it. So let's try this one here, and we have, it says, given the expression represents the area, find the side length of the square. So we know this is a square, so all sides are the same. So I'm going to go ahead and look for common factors. Don't see any, so I see that the first term and the last term are both perfect squares. If I take their square roots, it's 8x and 8x. 25 would be 5 and 5. I know both sides are positive because they multiply to make a positive, add to make a positive. So let's check it, see if it works. See, 40x is one of them. Well, if you just check the other one, it's going to be the same because they're the same numbers being multiplied. So 40x and 40x add to make 80x. So I know it. I know the side length is 8x plus 5 units. Don't know what the units are, so I'll just write units there, and that's the side length. So let's take a look at the next example there. Same sort of thing. So again, we've got a perfect square and a perfect square, so I'll factor it that way. 3y times 3y makes 9y squared. And 4 times 4 makes 16, but I have the wrong sign there. See, it's a minus sign there, so I need to make sure both signs are negative. So I'm going to fix that real quick. Change those to negative signs. And it should work out. So let's see if it does. Negative 12y. I've got another negative 12y, and those two do add to make negative 24y. So it works. So I would say the side length is 3y minus 4 units. So the last one here, no common factors. I see a perfect square, and the last term's a perfect square too. So I'm going to factor it as two binomials. 2c and 2c make 2c squared. Positive 9 and positive 9 multiply to make 81. Again, the reason why we use the same numbers is because our guess is that it's a perfect square trinomial. And so that's why we end up going with those. And so 18c and 18c, sure enough, add to make 36c. So you see, whenever those are first and last terms of perfect squares, that's what you look for. You look to see if it is a binomial being squared or a perfect square trinomial. So those are the perfect square trinomials. Let's take a look at another type. This is called a difference of squares. See, we still have perfect squares, but now we've got a difference. So difference means answer to a subtraction problem. So difference of squares is what we see here. So the difference is right here, and the perfect squares are m squared and 49. And so if that's the case, the reason why we don't see that middle term is it cancels out. So what we're left with is a sum and a difference. So what you do is you take the square roots of those numbers, you put them inside the first and last terms of each of the binomials, and then you just have opposite signs, because negative 7, positive 7 multiply to make a negative 49, but you'll see how the outside terms, if one is negative and one's positive, make a negative term and a positive term of the same value, so they'll cancel out and make 0. That's why you don't see that middle term. So that's the answer, m minus 7 and m plus 7. So when you see a binomial being squared, it can factor. It's long as we've got perfect squares as the first and last term. So we'll go ahead and do that. We've got 2a minus 5, and we'll try 2a plus 5, because both of these are perfect squares. And you see how the outside terms and the inside terms, or outside and inside, cancel each other out. Negative 10a, positive 10a, and they make 0. And so we see that the first and last terms multiply to make the negative 25 here, and 2a and 2a make 4a squared. So it works. And that's what we look for. Now sometimes you won't see perfect squares. So if you have a binomial that doesn't have perfect squares, see if there's a common factor. So I see 2 goes into both 50 and 8. So I'll pull the 2 on the outside and see what's left over. I've got 25g squared minus 4. Now both are perfect squares, so that tells me I can factor it. So I know it's going to factor 2. A 5g minus 2 and a 5g plus 2. And so again, you can see how the negative 2 times 5g makes negative 10g, and the 5g and 2 make positive 10g, and those will cancel out to make 0. So that's the answer. So again, it's just a strategy of factoring whenever we see a binomial, and the only binomials that are going to factor as two binomials is going to be one that's a difference of squares. So I don't see a difference of squares here, so I'm going to go ahead and take out a common factor. So I do see 6 goes into these two numbers, so I'm going to divide both of them by 6. So I'll put 6 on the outside, and I've got 4e squared minus 9 left over. Now I know I can factor further because I've got a difference of squares. So it's going to factor as 2e minus 3 and 2e plus 3. And it'll work because you see how negative 6e for the inside terms, positive 6e for the outside terms make 0 when I combine them together. So I know I have the correct answer. So that's what you're going to see on tonight's assignment. Good luck.